Hello, you're very welcome to this video on Scientific Form. There are many good videos available on YouTube. I'm Seamus Ballieu, and this video is for science and electronics students at Dundalk Institute of Technology. We'll also examine some other aspects of powers as well. So we'll make a start. So we're interested in looking mainly at powers of 10. So a little review. 10 by 10 by 10 is 10 to the power of 3, and that's equal to 1,000. Now, if we keep dividing by 10, the following scheme evolves. 1,000 divided by 10 gives 100, which is 10 squared, 10 tens. Divide 100 by 10, we get 10 equals 10 to the power of 1. 10 divided by 10 is 1, and 1 is the same as 10 to the power of 0. 1 divided by 10 is 0.1, and that's equal to 10 to the power of minus 1. 0.01, 10 to the minus 2, and 0.001 is 10 to the minus 3. So you can see as we divide by 10, the power decreases by 1 each time. And then in turn, we also know that 0.1 is the same as 1 over 10, 1 over 10 to the power of 1, 0.01, 10 to the minus 2, is the same as 1 over 100, 1 over 10 squared. And similarly, 10 to the power of minus 3 is the same as 1 over 10 to the power of 3, which is the same as 0.001. So basically, minus in the power indicates 1 over 10 to the equivalent power, only it's now positive. So why do we do scientific form? So it's a way of representing numbers that are very small. So for example, this case here, we've got 0 point followed by 11 zeros, 1, and that's equal to 10 to the minus 12. So there's a total of 12 zeros, including the one in front of the 0. Or we could view it that we move the decimal place over by 12 places, and it becomes 1.0 by 10 to the minus 12. So officially in scientific form, the number would read 1.0 by 10 to the minus 12. Scientific form can also be used to represent very large numbers. So if we got 1 multiplied by 10 15s, so that's simply equal to 10 to the power of 15, or being very technical, 1.0 by 10 to the 15. Again, you see, that's the decimal place there at the end of 1 by 10 to the power of 15. But to get it to scientific form, you can view the decimal place being moved over by 15 places to 1.0 by 10 to the 15. So again, just to highlight this fact here, what does a negative power mean? 10 to the power of minus 6. So you can view that negative power as 1 divided by something. 1 divided by the equivalent power of 10, in this case 10 to the power of 6, where the power is positive. So basically 10 to the minus 6 is 1 divided by a million, 1 divided by 10 to the power of 6. Okay, so we've been talking about powers of 10. So our normal number system, we can call that the decimal system. So it's slightly independent of a decimal point. It's decimal because there are 10 digits starting at 0, running up to 9. And obviously you can see how the 10 digits evolved, coming from the Latin for finger. So we have 10 fingers. So that would have been the original counting machine. The binary system has only got 2 digits, 0 and 1. The octal number system has 8 digits, 0 up to 7. And those electronic students will also be considering hexadecimal system that's got 16 digits. So how does scientific form work? We've kind of given you a little hint already. So the first part of the number in scientific form is a number A, and A is between 1 and 10. It can include 1, but it's not 10, so it could be 9.99. So any number between 1 and 9.999, let's say. So it's A by 10 to the power of some integer. So an integer like 3, 4, 5, 6, or minus 2, minus 3, minus 4, and so on. So here are two simple examples. Here we have 8 million, 8 by 10 to the power of 6. 8 multiplied by 10, 6 times. And here we have 0.00008. Again, that's 8 divided by a million, which is 8 by 10 to the minus 6. So you can view the negative power as dividing by 10. That's another way to view the negative power. So it's 8 divided by 10, 6 times in this case. So again, this is just another way of looking at the scheme. So in scientific form, we only have one digit in front of the decimal point. So it's something times, and you can have as many digits as you like after the decimal point, multiplied by 10 to some power, and the power is an integer, as we said. So for example, the power could be minus 6, or it could be 4. So let's look at an example. So write 237 multiplied by 10 tens. In scientific form, there are 10 zeros there. So again, we want the first part of the number to be 2.37. There's only one digit in front of the decimal point. So when we change this number to scientific form, it'll be 2.37 times 10 to the power of something. So before we start the process, imagine our number just written out there, and we just say it's 0.0. So we didn't have the decimal point included originally, but just for the purposes of thinking of this process, what we want to do is we want the first number, or the first part of the figure in scientific form, to be 2.37. So how many places do we move that decimal point? So we move it 3, another 3, another 3, and another 3. So we're going to move it 12 places. So that means our number is going to be 2.37 by 10 to the power of 12. So 2.37 by 10 to the power of 12. So we've moved the decimal point from the end up to here. So that number is exactly the same as the number that we started out with. So we've changed that number to scientific form. Another thing I suppose to view is if the number is large or bigger than 1, the power in the 10 will always be a positive integer. If the number is less than 1, the power in the 10 will be negative. We'll see that. So here's an example. 0.000, so many zeros there, 576, and we want to write that in scientific form. So again, we want to move that decimal point over so that the first digit is 5, so the first part of the number is 5.76. So it's fitting into this scheme always. The number is between 1 and 10. So 5.76, and we'll count the zeros, or count the places that we moved. So the decimal place got moved 14 places, or another way to view it, we had 14 zeros, counting the one in front of the decimal point. So in scientific notation then, it's going to be 5.76 by 10 to the power of, and this is a number that's much less than 1, so the power is going to be negative 10 to the minus 14. So there we are. Okay, so here's some questions for us to be thinking about now. So change these numbers from decimal form to scientific form. So again, we're kind of looking at getting the first part of the figure in scientific form. So we'll just do that for the whole of them first. So this one here, the first part of the figure will look like 6.789 by 10 to the power of something. This one will look like 5.986, 1.78, 7.85, that one doesn't change, 8 point something, 5.68. So we have an idea what the first part of the figures will look like in scientific notation. So let's start with the first one. So again, we insert our decimal point here at the end and we count the number of places that we move it. So it's going to be 9 by the looks of it. So that's going to be 6.789 by 10 to the power of 9. So again, just to look at the complete picture when it's finished. So that figure there is 6.789 by 10 to the 9. This is a figure less than 1, so it's going to be by 10 to the power of minus something. The first part is going to be 5.986. So many places does the decimal get moved? It gets moved 5 places. So you can kind of see that fairly easy. So 5.986 by 10 to the minus 5. So moving on to the next one, we've got 0.178. Again, it's going to be by 10 to the power of minus something, and it's going to be 1.78. So 1.78 by 10 to the minus 1. The next one is 785.36. So again, that's going to be, it's a figure bigger than 1. So it's by 10 to the power of a positive, and the decimal place gets moved 2 places. So 7.8536 by 10 to the power of 2. So we take the next ones together. So 7 is 7.0 by 10 to the power of 0. That should be 0 there. 10 to the power of 0 is 1. 0.8 is the same as 8.0 by 10 to the minus 1. 5.68 by 10 to the minus 3. So there's our complete picture. So again, just checking that 7 there. That's 7.0 by 10 to the 0. So you can see how the first part of the number in scientific form always is a between 1 and 9.99, so 6.789 and so on, by 10 to the power of various powers. If the number is bigger than 1, the power is positive, less than 1, the power is negative, less than 1, power negative, and so on. So that's decimal form, the usual counting system, and this is scientific form. Okay, so we do the opposite now. We change a bunch of numbers from scientific form to decimal form. So looking at the first number, 2.75 by 10 to the minus 7. So negative power in the 10, we know that the number is going to be less than 1. Another way to view this is we're going to divide by 10 7 times. 10 to the minus 7 means we divide by 10 7 times. If we divide by 10 once, we have 0.2. And then dividing by 10 another 6 times, it'll generate 6 zeros and then the decimal point. So the number then looks like 0.60275. 2.75 by 10 to the 8, we're multiplying by 10 8 times. So 2.75 multiplied by 2 tens gives us 275, and then we have 6 tens left to multiply, so that'll be 275 followed by 6 zeros. 3.89676 by 10 to the minus 8. Again, we divide by 10 8 times, so that will be 0.70389676. Or just to view it simply, move the 0 in front of the 3 and divide it by 10 once, and then 7 more zeros, and then your decimal point. 3.89676 by 10 to the 14. So multiplying by 10 5 times takes us to there. And then we have 9 zeros after that. So the number then looks like that there. So there's 9 zeros, so plenty of digits. 7.63 by 10 to the minus 2. Divide by 10 twice. So 0.0763. 8.79 by 10 to the minus 1. So it's simply 0.879. Divide by 10 once. 5.4 by 10 to the 0. We neither divide by 10 nor multiply by 10. So the answer is going to be 5.4. Or remember, we said 10 to the 0 was 1. So 5.4 is our answer. And then this one, 0 followed by 4, followed by 4 zeros, 5 zeros, 86086. Sorry, that should be 4 zeros. Let me just clarify that. So we're dividing by 10 5 times. Divide by 10 once, brings you 0.8, and then you divide by 10 4 more times. So it's 0.0000086. 7.68 by 10 to the 12. So 768 multiplied by 10 10 times. And there we go. Now, let's just look at multiplying powers. So if we have 100 multiplied by 1000 equals 100,000. That's 10 to the power of 2 by 10 to the 3 equals 10 to the 5. So notice we've got the base of 10 in both cases. So what do we actually do to the powers? We add the powers together. 2 and 3 is 5. Or effectively, we've got 2 tens there multiplied by 3 tens, giving us a total of 5 tens. So you can understand why you add the 2 and the 3. 10 to the minus 3 by 10 to the 9. So basically what we're doing is Imagine we're multiplying by 10 9 times, and we're dividing by 10 3 times. So overall then we're left with 10 multiplied by 7 6 times. So our answer is going to be 10 to the 6, or again you just simply add the powers. Minus 3 and 9 is 6, so 10 to the 6 is our answer. So here's a few examples then. If A is 5.67 by 10 to the minus 12, B is 7.86 by 10 to the 5. How do we multiply those two numbers together? They are two numbers in scientific form. So you can multiply the first part together and then multiply the powers of 10 together, and we get our answer. So 5.67 by 7.86 gives us 44.57 by 10 to the power of, and you multiply 10 to the minus 12 by 10 to the 5, we get 10 to the minus 7. So basically what we're doing is we're multiplying four numbers together, and the order in which we multiply the numbers doesn't matter particularly. So what we choose to do is to multiply those two bits together first, and then multiply by the powers of 10. So 44.57 by 10 to the minus 7. Now that number there is not in scientific form, because the first part of it is not 4 point something. So there's 10 to the minus 7. We're dividing by 10 7 times. What would happen if we divided by 10 once? Divide that there by 10 once. So that's 4.457. And now it remains for us to divide by 10 6 times. So that form of the figure is equivalent to that, but this is now in scientific form. So essentially, if you divide by a 10 less, you can divide the 10 into the 44 to give you 4.4. So that those figures are the same, even though they look in different form, but this is scientific form. Example 2, again, two similar examples, two similar numbers in scientific form. C times D, multiply the coefficient bit. So 3.86 by 6.98 by 10, and now you're adding two powers there because you're multiplying. That's 10 to the minus 11. So it's 26.96 by 10 to the minus 11. Or you can view it as 3.86 multiplied by 6.98. And instead of viewing it as being multiplied by 10 to the minus 3, you can view this as being divided by 10 3 times and dividing by 10 8 times. So the net result is you're dividing by 10 11 times. But again, that's not in scientific notation. So if you choose to divide the 26 by 10 once, that would give you 2.694, and then it remains to divide by 10 times. That number is now in scientific form. So our third example, F 5.76 by 10 to the 7, G 9.03 by 10 to the 11. So multiply the 5.76 by the 9.03. So that's 52.01 multiplied by 10 18 times. Now that number is not in scientific form, but 52 by 10 to the 18 is the equivalent of 5.2 by 10 to the 19. So if you view it backwards, 5.2 by 10 to the 19, take one of those 10s back there. That's 5.2 by 10 is 52 by 10 to the 18. So that's the equivalent of the 52 by 10 to the 18 in scientific notation, 5.2 by 10 to the 19. Now, we look at division of powers. We're going to use this now in a minute. 10 to the power of 7 divided by 10 to the power of 3. What do we do with the powers? You take them away. 7 take away 3 gives you 4. So basically, again, you're multiplying by 10 7 times. You're dividing by 10 3 times. The net result is we're multiplying by 10 4 times. So A 5.67 by 10 to the minus 12. B 7.86 by 10 to the 5. A divided by B. So we divide the coefficient bits, the numbers in front of the 10 to the powers. So 5.67 divided by 7.86, and that gives us 0.721, and then it's 10 to the minus 12 divided by 10 to the minus 5. So again, it's minus 12 minus 5. So that gives us 10 to the minus 17. So 0.721 by 10 to the minus 17. So that's 0.7 divided by 10 17 times. That's equivalent to 7.21 divided by 10 18 times. So because that was multiplied up by 10 once more, to give 7.21, then to compensate, you divide by 10 18 times. So again, the division, 10 to the minus 2, 12. So effectively, you're dividing A by B, and you divide 5.6 by the 7.8, multiplied by 10 to the power of something. So effectively, the overall quantity is divided by 10 12 times, and then you're dividing by 5 again. So the net result is you're dividing by 10 17 times. C, 8.37 by 10 to the minus 9. D is 5.62 by 10 to the minus 6. So 8.37 divided by 5.62 multiplied by 10 to the power of something. And now it's 10 to the minus 9 divided by 10 to the minus 6. So maybe we just step aside and just look at that for a minute. There's kind of a double negative going on there. So again, let's remind you, 10 to the minus 6 is the same as 1 over 10 to the 6 equals 1 over a million, 0.000001. Now, 1 over 10 to the minus 6. What's 1 over 10 to the minus 6 equal to? A minute ago we had 10 to the minus 6. But let's look at 1 over 10 to the minus 6. Well, that's equal to 1 over, and we just saw a moment ago that 10 to the minus 6 is the same as 0.000001. And what is 1 divided by 0.000001? It's equal to a million, and that's equal to 10 to the 6. So 1 over 10 to the minus 6 is equal to 10 to the 6. So effectively, if this comes up over the line, it becomes 10 to the 6. Likewise, in the reverse earlier on, we had 10 to the minus 6, and then that went under the line and became 10 to the power of 6. Okay, so back to our example. 10 to the minus 9 divided by 10 to the minus 6. So effectively, that's 10 to the minus 9 multiplied by 10 to the 6. Because dividing by 10 to the minus 6 gives you the net result of multiplying by 10 6 times. So dividing by 10 9 times and then multiplying by 10 6 times has the net result that you're dividing by 10 3 times. Or effectively, go back to the original rule, when you divide, you take the power away. So minus 9 minus minus 6 gives you minus 3. Okay, so here we have the metric prefix scale. So these are units that will be used by engineers in science. So for example, if we had 1 meter, 10 to the 0 corresponds to 1. So suppose you had 1 meter, then if you had 1,000th of a meter, 10 to the minus 3, you'd say you have a millimeter. If you had a millionth of a meter, you would say you've got a micrometer. 10 to the minus 9 meters, nanometer, picometer. Then what would happen? Again, we've got 1 meter. Would we scale it up to 1,000? How many meters have we? We have 1,000 meters, but we also call that a kilometer. 1,000 meters is the same as 1 kilometer. A million meters would be a megameter. Now, we don't really do that metric, but maybe in engineering, in ohms. So supposing you have an ohm, and then you have a million ohms. A million ohms is the same as a mega ohm. And in computing, we have bytes, kilobytes, megabytes, gigabytes, terabytes. So just to give you a feel for the different units there. Okay, same thing again. If it's micro, it's 10 to the minus 6, milli, 10 to the minus 3, nano, pico, and then femto, 10 to the minus 15, and then kind of going up again along there. Centi, 10 to the power of minus 2, deci, 10 to the minus 1. And again, in computing, if you have 10 to the 6, you refer to that as mega. Now, technically, those people that are knowledgeable in computing, there's actually a few more bytes. It's not quite 10 to the power of 6. We're only using these here just to get the prefix, the mega and the gigabit going. But in computing terms, a megabyte actually is more to do with powers of 2. But you've got mega, giga, tera, peta, exa, zeta, and iota, just to entertain you there. Now, more importantly, in engineering notation, this is more geared to electronic students. Supposing you have a capacitor and it's 57 microfarads. How many farads is that? So we saw a few minutes ago that a microfarad is a millionth of a farad. So 1 microfarad is 10 to the minus 6 farads, or 1 farad is the same as a million microfarads. So 57 microfarads is the same as 57 by 10 to the minus 6 farads. Now that number is not in scientific form, but it's in engineering notation. So engineers often refer to 57 microfarads as 57 by 10 to the minus 6 farads. So engineers tend to go 10 to the minus 3, 10 to the minus 6, 10 to the minus 9 and adjust the figure in front accordingly. 98 nanofarads. Again, 1 nanofarad is 10 to the minus 9 farads. So the 98 nanofarads is 98 by 10 to the minus 9 farads. Okay, so here we want to change 6.7 kilo ohms to ohms. So 1 kilo ohm is the same as 1,000 ohms, or 10 to the 3 ohms. So 6.7 kilo ohms is equal to 6.7 by 10 to the 3 ohms. Change 78 by 10 to the minus 3 amps to milliamps. And we know that an amp, so we know that an amp is 1,000 milliamps, or we know that 1 milliamp is 1,000th of an amp, or 1 milliamp is 10 to the minus 3 amps. So therefore 78 by 10 to the minus 3 amps is the same as 78 milliamps. So looking at all those units then, all those units that look a wee bit like scientific notation are not actually scientific form, but they're in engineering notation, and this is usual for an engineering context. It's because, well, that one is scientific notation because it's 6 point something by 10 to the 3. That's not scientific, and that there is not scientific notation. Okay, so we application in science. For science, there's one large quantity. It's known as the mole, and 1 mole contains 6.022 by 10 to the 23 atoms or molecules. So we look at an example of that. 1 mole of oxygen gas, O2, contains 6.022 by 10 to the 23 molecules, and it weighs 32 grams. If you look up the periodic table, each oxygen is 16. So 1 mole of oxygen gas, O2, is 2/16 is 32 grams. A mole usually weighs the molecular weight in grams, or the atomic weight in grams. So if we look at example 2, 1 mole of H2O water contains 16.022 by 10 to the 23 moles. A mole of any substance always contains exactly the same number of atoms or molecules. That number doesn't change, but the weight does. And the weight this time corresponds to the molecular weight. And the molecular weight of water is 16 for the oxygen and 1 for both hydrogens. So the molecular weight of water is 18. So 1 mole of water weighs 18 grams. And one more example to finish up. 1 mole of helium gas contains 6.022 by 10 to the 23 atoms. Helium gas is inert, it's not a molecule, it goes around as its own atoms, and the mole of helium weighs 4 grams. So we hope you've enjoyed the video, and we look forward to seeing you the next time. Thank you very much.